So today we're going to study new functions. Actually, it's not a very brand new function. They're a combination of the exponential functions, but their behavior like trigonometric functions, and we call them hyperbolic trigonometric functions. Okay, the first function is hyperbolic sine x. This is going to be defined to be by this e to the x minus e to the negative x divided by 2. And then hyperbolic cosine x is going to be the sum, part sum of those two terms. And similarly, you can define hyperbolic tangent x, which is hyperbolic sine x over hyperbolic cosine x. Then hyperbolic cotangent x, and you just turn upside down this too, right? And then similarly, you can define hyperbolic cosecant x and the secant x. So very similar to the geometric functions. Okay, we have then the cosecant. Yeah, this is called SCHXX, and 1 over hyperbolic cosine x. All right, now there's a reason we want to denote them by using sine cosine here, but put an additional letter h. Okay. For example, there's some identities we need to know. Okay, hyperbolic sine x squared, and let's see, I'm going to do this one. Yeah, write hyperbolic cosine x first. Hyperbolic cosine x, okay, minus hyperbolic sine square x is going to be 1. Okay. And you compare with the sine cosine. Cosine square plus sine square equals 1. Now here's a minus. Okay. Then if you both sides divide by cosine, hyperbolic cosine x, what you can get, right? If you divide by cosine x, okay, then this will be 1 hyperbolic cosine x. This will be hyperbolic tangent x, and this is going to be 1 over hyperbolic cosine x square, right? So which should be equal to secant hyperbolic secant square x. Okay, those two identities essentially the same identity, but a different form. Okay, so this is what we needed to know. Then once you have a function, you want to talk about derivatives, right? So you're trying to find the derivative. The derivatives also behave very similar. So the derivative of hyperbolic sine x, right? How do you differentiate? This is e to the x minus e to the negative x. Just differentiate the exponential function. So the first term is e to the x. The second term, when you differentiate e to the negative x, you get e to the negative x times negative 1, so it becomes positive here. So this is nothing but hyperbolic cosine x. Okay. So when you differentiate, you get another function. And similarly, okay, and you get hyperbolic sine x, but not negative. Okay, remember the derivative of cosine x is negative sine x, but here you never get a negative. Okay, plus e to the negative x. So when you differentiate the second term, you get a negative sign. So this is a hyperbolic sine x. Okay. If you forgot those formulas, you just redo it quickly. You can figure it out. But at least you should know the derivative of e to the x, right? And there's a definition of this hyperbolic function. All right. Now let's guess what is the derivative of hyperbolic tangent x. Hyperbolic tangent x. Okay. Remember, derivative of tangent x is going to be what? It's going to be secant square x. Okay, so it's possible it will be hyperbolic secant square x. Okay, it's possible, right? So let's find the derivative of this. Right, let's find the derivative. Yeah, so this is going to be by the chain rule, right? Here's hyperbolic cosine x, hyperbolic sine x. So you already know the derivative of the one on the top. Okay, so the derivative of hyperbolic sine x is going to be hyperbolic cosine. Then you multiply by the one from denominator, so it's square, minus the derivative of a hyperbolic cosine x is going to be sine x, hyperbolic sine x. So that's just a square. Okay, so from here you can tell that, right? The one on the top is 1. And so it's hyperbolic secant square x. Okay? Yeah, hyperbolic cosine square x minus hyperbolic sine square x is equal to 1. So those are the derivatives. Now, how about the inverse? Okay, so take a look at the graph of y equals hyperbolic sine x. This function is an odd function. Okay, it's harder to draw it. I think this is an odd function. When x is negative, it's negative. When x is positive, it's positive. So going through this point, origin. Okay, and I guess it looks like a parabola. It's this 1/2 as a half. Okay, so this is the increasing function. So you can find the inverse, reverse the procedure. You get to this. X should be the hyperbolic inverse. The inverse of hyperbolic function. Okay. Then, if we exchange the two variables, you get a formula for the inverse of hyperbolic sine function. Okay. And you can draw the graph for that, right? So now our next step is to find the derivative. So it's a good exercise. Okay, find the derivative of hyperbolic sine x. Okay, I'm going to show you 2 different ways to do it. Yeah, we have a quiz today. We'll do the same way as last time. Okay. Yeah. So the quiz will be released on Canvas in the assignment area. So when you see quiz 2, just click that and you open. Not right now. You cannot see that. Okay. It will show up at 11:30. Okay. And also I will post it here just in case you're not able to get access. All right. So how to find the inverse? Well, sometimes you can find it. The formula. Okay. And right, we know that the y equals e to the x. So we already introduced a new function for the inverse of the exponential function. So we can use that to probably can express the inverse of hyperbolic sine x. Okay, let's do it. So we have, right, we're trying to solve for x, right? So this is we're trying to solve x. So what we get here is e to the x minus e to the x. Great. I'm trying to find x. Am I able to do that or not? Well, it's possible. Okay, you multiply both sides by 2. Then you multiply both sides by e to the x. Okay. So 2y e to the x equals e to the 2x minus 1. All right. So then you have a e to the 2x minus 2y e to the x minus 1 equals 0. This is a quadratic equation. I'm trying to find e to the x first. Okay. This is a quadratic equation, something square minus 2y, something minus 1 equals 0, right? So this is a quadratic equation. So e to the x is going to be negative 2. Negative b is 2y plus or minus b squared minus 4ac. So it's going to be 2. So plus, right? I think this is going to work by y squared plus 1. Yeah, divided by 2. Now this 4 can be taken out, right? 4 can be taken out. So this 2 cancels out. It's just y plus minus y squared plus 1. All right. This is e to the x. E to the x has never been negative. So clearly you cannot choose negative sign, because if y minus square root y squared plus 1, this will give me negative. So that's why e to the x is y plus this. Right, that's the only choice. All right, so we can find the inverse, right? Then x is going to be natural log y plus, not too bad. Okay, this is our inverse. So my conclusion is, yeah. My conclusion, if we want to use a variable for use x for the variable of the inverse function, then you conclude that all right. Now this is another expression. Okay, you can define the inverse function in this form, no problem, right? So actually, you can express the inverse function in terms of natural log. In terms of natural log. Okay. Okay, so let's go back again. Okay, y equals e to the x. Then you have end up with the the inverse function, and here's y equals hyperbolic side. Then the inverse function is going to be natural log of x. Okay. This hyperbolic function is actually e to the x minus e to the x. And you can use a you can use a we don't have a new name for the inverse function, okay? And it's not like e to the x, the inverse is by natural log of x. We just simply write like this, right? And I cannot use a if you already use an e here, I cannot use an e to the negative, so it's an inverse function, no. So you have to choose a new notation, because this is already, it's not in the function symbol, okay? This is not in the function symbol. This is a e to the x already, it's easy number. And here is a sin x. Sin h is the name of the function, so you can use that one for the inverse. Okay. All right. So now you can find the derivative, right? The derivative of this function, and by the chain rule, it's going to be, first of all, you put it in the denominator, then you differentiate the function here. It's 1 plus, right? How about the derivative of the square root x plus 1, right? This I just give you the answer here. Right? When you differentiate the square root x squared plus 1, you get x over square root x plus 1. Now you simplify it. Okay, you simplify it. You combine those two terms on the left and the right hand side. You get square x plus 1 plus x. And you realize that this two cancels out. Wow. Finally, you only get x squared plus 1. So that's great. That's what we want. And we find out the reason we want to introduce the hyperbolic sign x, now it's pretty clear. We want to find an antiderivative of 1 over square x squared plus 1. Okay, so right, so that's why we have, let me summarize what we discover. Okay, or you can write to like 1 plus x. Okay, so this is the integral. Therefore, if you in the future, if you see square root of 1 over square x squared plus 1, the antiderivative is this function. Okay, I always want to do comparison. Remember, I had a question, right, at the end of the last class. So what is the antiderivative of this, right? 1 minus, right? This is remember, this is just the derivative of the inverse function, sine x, right? If I say, I said that if I change in minus to plus, then what we get, right? So now we have, right? If I change it to the positive sign, then I should use hyperbolic sign, inverse of hyperbolic sign. So there's a corresponding scale. There's corresponding here, right? All right, but we find the formula. We find the derivative of the inverse inverse of sine x is using the formula for the derivative inverse function, right? Well, here we just we did not use that formula. We directly find that we find the formula for the inverse function first, then we differentiate. Okay. But we can get this formula in the same way. Okay. So this is another way we're trying. Okay, the derivative of this function by the formula is 1 over the derivative of hyperbolic sine, right? Remember this formula, right? So, but the derivative of hyperbolic sine is going to be hyperbolic cosine. Okay, and the next question is how can we get rid of a hyperbolic cosine, hyperbolic sine? Yeah. How do we do that, right? Think about this. All right, so we can do a similar way to do, right? We can say, okay, let y to be hyperbolic sine x inverse, right? And we want to find out hyperbolic cosine y, right? Basically. Okay, but we know that this will be, x will be hyperbolic sine y, okay? And I think there's no restriction on that. But this should have the same sign as x, but it's okay. We only have one here. It's not like an angle is between, there's no angle here. Okay. But there is a relationship, right? Right? And that is going to be 1, right? Okay. So in order to find this, I needed to move the other term to But the hyperbolic sine y is going to be x. So it's going to be 1 plus x squared. And that's a square, right? Then you solve for hyperbolic cosine. Now, hyperbolic cosine is always a positive function. Okay, so that's why you never get a negative. Okay, so it's done. Okay, so therefore, if this is a part, right? So therefore, you can get the derivative. This is a much quicker way. Okay, so that is a quick way to get. All right, before we move on to the derivative of the other inverse function, let's take a look at the following example, a couple examples, okay? Yeah. The first one is a pretty tricky problem. You let f of x to be hyperbolic in the nature of x. Okay, find the find the derivative of this function. Okay. I think the best way to solve this problem is to simplify the function. Try this first, and it can be done. How do you simplify? It's going to be by the definition of hyperbolic sine x. It's e to the natural x minus e to the negative natural log x. And so you can get rid of the e as the natural log here. Right? Yeah, let's rewrite again. It's an e to the natural log x to the negative 1, right? So the first term is x, and the second term is x to the negative 1 divided by 2. Now it's easy to differentiate this, right? So the derivative is going to be, the first term is 1, the second one is minus. Okay, so that is the answer. You can write it in a slightly different way. You can write it like this. Right. So this is an answer. Right. So when you get an expression, just you look at it first. Are you able to simplify a little bit before you find the derivative? Another problem is hyperbolic sine and square x and square x dx. And clearly, for this problem, you have to use a substitution, right? So you let a to be square x, then you try it, right? Try this substitution to see if we can evaluate the integral. So du equals, when you differentiate square x, it's 1 over 2 times square x and dx, right? 1 over 2 times square x. So then you go back, this part is going to be twice of du, so hyperbolic sine u and twice of du. Right, now the antiderivative of sine u is going to be cosine, hyperbolic cosine u. And then you replace u by square x, and you get answer. Okay. Right, our next problem will be the following. Okay. Let's try this, okay? So that is going to be square root of x times 1 plus x and dx. Wow, this looks pretty complicated problem, right? And we never heard that before. So then the substitution is pretty tricky. So what do we have to do? Right. I use the following substitution. Let x to be u squared. I'm sorry. Okay. Yeah, let x to be u squared. We try this first. Or u equals square x. Then I'm not sure where we'll go for this, right? Then dx is 2u du, right? And that's fine. And the integral here, since x is equal, right? So of course x must be positive. So let's assume we use positive here, okay? X is positive, okay? So square u is going to be square u, right? Square. And here's 1 plus u squared. And this is a 2u du. And what do you get? U's canceled out. Great. And then you only get, square u square is going to be u, right? So u cancel out. So then you get this integral. And we know that this is going to be hyperbolic sine u plus, right? And then what is u? What's hyperbolic sine? U, what is u? U is going to square x. Okay. So, we successfully do. We'll find the value of this integral. All right. Now, how about hyperbolic cosine? Cosine. All right. Hyperbolic cosine x is not a. Yeah, let's study hyperbolic cosine x. This function is not an even function. It's not an increasing function. This function looks like that, the graph. Okay, so we have to put a restriction on x in order to find the inverse. Right. So clearly, x should be, we can assume x is positive. Right? Then you can solve for x in terms of what? Okay, so you get the inverse function. Now the question is, what is the derivative of that? Yeah, what is the derivative of that? So y value here is power greater than 1. And y value. So you can get this, right? So let's find the derivative. The derivative of this by the formula, right? Hyperbolic cos as the derivative of hyperbolic cosine and okay. Yeah, we can only consider one piece in order to define the inverse. Right? Right, so this is going to be hyperbolic sine. All right. Then we have the identity. Remember, right? The identity is hyperbolic cosine square y and minus hyperbolic sine square y equals 1. I think hyperbolic sine y equals, right? Using this identity. So, so from above, when y equals cosine, yeah, this is a hyperbolic sine y, right? When y equals hyperbolic cosine x, right? So what do you get? And this is gonna be x. Okay, when we are replaced, right? Now the question is, what is the sign of a hyperbolic x? When you solve it, we know that this must be positive. Okay, so that's why just x squared minus 1, just squared. And from the definition of this output, this will be always a positive number, right? This is a positive number. This is always positive. That's why hyperbolic sign is positive. That's why you take a positive sign of a square, x squared minus 1. So, well, we get the following derivative. Yeah. So it's not similar to the it's not similar to cosine inverse arc cosine x. Yeah, that's a slight difference here, right? Yeah, let's do the comparison. Otherwise, it's harder to memorize all of them. Okay, this is going to be 1 over x squared plus 1, right? And this is and then you have this, right? Right? And this is a pattern. But for the derivative of inverse function, right? It's going to be square 1 minus x squared. And here, the derivative of hyperbolic cosine x is going to be negative. So essentially, there's no difference between those two when you try to evaluate integral, right? Different by negative sign. But here's quite different. Here's quite different. There are those two expressions on the left-hand side. They not have the opposite sign to each other. At the very beginning, I thought, maybe just negative 1 over square root of x squared plus 1. No, actually, it's x squared minus 1. Okay. So when you see square 1 over square x squared minus 1, and you think, yeah, this is necessary, this formula. Okay. It's not like here on this side, on the right-hand side. You don't need a hyperbolic cosine x. You just need the hyperbolic sine x. Okay. No, you don't need the arc sine x. Don't need the arc cosine x. You just need the arc sine x. Okay. So you can, yeah, let's see what you can write as this. But here on this side, you only have this formula. And then to deal with this, then you have to use inverse of cosine x. Okay. All right, so I just get more formulas, but since you have the open textbook, sometimes you say, okay, that's great. I don't need to memorize this one. I just use it, right? That's okay. All right. Now let's focus on hyperbolic tangent. Okay. are we are we able to find the hyperbolic tangent x? So E is going to be, yeah, y equals hyperbolic tangent x. This is going to e to the x minus e to the negative x, e to the x plus e to the negative x, right? Now, am I able to find the formula for this? And what is this? This function is increasing or decreasing function. Well, if we already find it, then you don't need to check whether it's increasing or decreasing. Okay. So I'm pretty sure this is a function. Yeah. This is the graph looks like that. It's still increasing function. This graph looks like that. Okay. It's increasing. Okay. So you are able to reverse this procedure to get to the inverse function. Right. So this is going to be, yeah, this is going to be tangent, hyperbolic tangent x. Okay. And actually, you can find the formula. Right. If you don't want to find the formula, and there are two ways to do, right? So let's find the derivative of this, right? According to the definition, according to the formula for the derivative inverse function, this is going to be about, right? All right. But the derivative of hyperbolic tangent x is going to be secant, hyperbolic secant squared. Right? But we know that 1 minus, right, it's not inverse, just a square. Okay? Using this identity, in this place, put y here. What do you get? So you get 1 minus, right? We have a 1 minus, 1 minus hyperbolic secant square, and now I use a secant, so it's tangent. Yeah, change the secant to tangent. Okay. Yeah, you can move the switch to 2, right? So now you get the 1 minus x squared. So it's great. So the derivative of hyperbolic tangent x just equal to 1 over minus x squared. And this is a pretty similar to the hyperbolic tangent x inverse. It's going to be 1 over 1 plus x squared, right? Yeah, just change the x positive x squared to negative x squared. There's also another, for every inverse function here, hyperbolic sine, cosine, and the tangent x. You can always find the formula directly, the inverse function. Okay, so let's try to solve for x. Solve for the inverse function. Y equals, right, so e to the x minus e to the negative x, e to the x plus e to the negative x. So let's try to solve for that. Okay. So I have okay, then I multiply both sides by e to the x I get e to the 2x plus 1, e to the 2x minus 1. I even don't need to solve the quadratic formula. I just get y e to the 2x plus y minus 1. So I think it's better to move this one to here, the 1 to the right-hand side. So y plus 1 equals e to the 2x minus y e to the 2x. So it's 1 minus y e to the 2x. Right, finally, I get e to the 2x, and here's 1 plus y, 1 minus y, over 1 minus y. And in order to get x, I just solve for x. Okay. Or, yeah, this is the formula for the inverse of the hyperbolic tangent, right? So now you have y equals, and which is half of natural log 1 plus x, 1 minus x. Once you have this formula, you can differentiate. Okay. You can differentiate, you can get the derivative directly. So the derivative of this function is going to be half of the derivative of this. You can, this quotient you have to separate. Okay. Then you differentiate each term. It's much easier, right? Okay. So what I'm trying to do here, I have two different ways to find the derivative always. Because I can find the formula for the function, for the inverse function. I don't know using natural log. All right, so the derivative here is 1 over 1 plus x and minus 1 over 1. And they have all the negative sign, so it's getting negative 1 here. After you combine those two terms, and I get the 2 on the numerator. So divide by 2 is gone. So it's going to be 1 plus x, 1 minus x, which is also equal to the same. Okay. So we get exactly the same answer. Okay. Anyway, from now on, right, you can express it in this form plus c1. But if you don't like the inverse function for the tangent, hyperbolic tangent x, you can express it in another form, which is we already get it, right? We got this. The inverse function has another formula, right? Plus c. Yeah. We can also get this formula using different method. Using different method. Okay. Then you will ask, how do we define the hyperbolic cotangent? Right now, in the book, it does not mention that. Probably it's not necessary to really does not create any new stuff. Well, the derivative of high inverse function. Yeah, this is okay. There are several. Yeah, there's several ones. I just want to mention that it's in the book. Okay. So let's see what does the difference. We already got to the derivative of hyperbolic sine, the inverse of hyperbolic sine, and the inverse of hyperbolic cosine x, the inverse of hyperbolic tangent x. Okay. So the other formulas, okay, you can also find the inverse of a hyperbolic cotangent x. Okay, so this is going to be, you will get to the same answer. So I'm surprised, right? This is the same as a hyperbolic inverse of hyperbolic cotindex. Okay, so it's not yeah, you don't get anything new here, right? Okay, you probably can also find the formula for this, which is very similar to the only different by constant. Right? So this implies hyperbolic cotangent x and hyperbolic the inverse of hyperbolic tangent x. They are only different by constant. Right? They only differ by constant and plus a constant. So you have to figure it out, right? So otherwise, when you differentiate, you don't get the same answer. So all I have to do is just trying to see what are the possible values, okay, on the constant c. Yeah, the graph is pretty complicated. I'm not going to mention that, but anyway, you can get a constant c here. Well, so since we do not get any new function except this 1/1 minus x squared, so we're probably not going to spend time to trying to see cosine hyperbolic, the inverse of hyperbolic cotangent. Now we also have as a two formulas, you can define the inverse function of hyperbolic cosecant x, and you differentiate. Then you will get -1 here, and here's a plus x, square x squared plus 1. I think this is a new function. That's interesting. And then this one is slightly different. This x is 1 minus x. Okay. So so there's an additional term, x in front of this, right? In front of this. So if you if without x here, right? The second one, you know, the integral of that one function will be the inverse function of sine x or cosine x, depending on sine. Okay. All right, so those are the formulas we needed. No, okay. So I hope we still memorize some things, right? So if we look at the integral of, let's go to, because if we get integral, if we get this one, right? This can be hyperbolic. This is going to be the inverse of sine x, right? Inverse of function sine x. Okay, you can also use that as negative the inverse of cosine. Okay. Then use the same form. If I change the sign to the positive side, then you have to use the inverse of hyperbolic sine x. Okay, and there's no additional another term. Okay, plus c. Right, so now let's go to the next one. We have 1 plus 1 of x squared dx, right? This is the inverse of tangent x, okay? And this is also could be the cotangent. Okay. Yeah. That's a negative sign here. Negative. So sometimes it is not unique expression. Okay. So that's different by sign. All right. Then what else? Then you have, okay, I'm going to change it to negative x squared. And this one, right? This one has a two different. This one you can use the inverse Hamiltonian x. Right? You can also use the inverse hyperbolic cotangent x. Right? This one minus x squared. So what is next? Next, we're going to. All right, so now we have add the x to the front of the square root. Okay, if I add x to the square root of that, and then this is going to be the inverse of secant x plus c1, but it is also going to be negative cosecant x plus c2. All right, so how about wow, okay, so how about the next one, x? Do we have x and x squared plus 1? Yes. Okay. So if I change it to okay, if I change it to this, right? Then then this will be wow. Okay, this will be actually it's negative. Okay, of y inverse of like cosecant. Okay, plus c. What else we should know? Oh, inside the radicals, you have to have x squared minus 1, right? Not only just x squared, right? So all the possible cases, right? Inside here, it's going to be square root of, yeah, it's a right? So this one is just the inverse hyperbolic cosine x. Then you also have to have a term, how about put the x squared there, right? We get all of them, right? And this will be actually is going to be inverse of secant x plus c1, but this also can be negative inverse of cosecant x plus c2. Wow, if you have all of this based on the form of the function, these are integral, right? So we get all of them. How many functions do we have, right? How many formulas, right? Yeah, it's a long list. That's why we are forced to get to the inverse functions. You know, we yeah. Like inside the radical, you have x squared plus 1 and x squared minus 1, or have 1 plus x squared, 1 minus x squared. Then you outside the radical, you can multiply with x, multiply by x, or was that, or just nothing, right? So there are multiple possible ways to, yeah. There are multiple forms, different forms here. So now you have you can use those formulas to, after you simplify the function, you maybe end up with one of these functions inside the integrals. Then you just use the formulas given in the textbook. Okay, but I already show you how do we get those formulas. Okay, how do we find the derivatives? How do we find the derivatives? Yeah, we did some examples. How do we find the derivatives? Okay. All right. Secant, hold on. The fifth, that's a secant. Yeah, secant. Well, you can double check that. Okay, this is, wait a minute. Did I make mistakes? I think I made mistakes here. This is x squared minus 1. It's 1 not, yeah. It's x squared minus 1, not 1 minus x. That's a mistake. Already used. Confused. Okay. Yeah, x squared. Yeah, x squared minus, yeah, x times x squared minus 1. That's okay. I can double check. Wait, I don't see anything wrong. Secant, hyperbolic secant, 2 secant, secant x squared. Oh, let me check. 1 minus x squared. I think I typed it in. Yeah, my spelling. Yeah, it's going to be. Yes. So, okay, now it's correct. All right, so let's stop. Let's stop here and